Hello, can you hear me? I cannot hear you. Can you hear me? Bushfire propagation speed, combining the effect of wind and slope. This is the topic and the title of the presentation. This presentation can be considered as a follow-up of a presentation at Modsim 2015. The main work has been developed within a master thesis project which was finished in 2018. So it means 2 years before I didn't have a budget to travel to Australia, and thanks to pandemic just now I can do this presentation in a remote way. The model framework we started with and we want to retake was in terms of the Hamilton-Jacobi equation with a level-set function phi, where phi positive represents the unburned area, phi negative the burned area, such that phi equal to 0 marks the fire front. In the equation, the velocity function A depends on local parameters. The main obstacle was the lack of available data that would have allowed reasonable function adjustments. The reason to deal with bushfire propagation was, on the one hand, the work with the same model type in another application context, and on the other hand, the fact that bushfires are a relevant phenomenon in Chile. That other application is a modeling and simulation of foam injection in petroleum reservoirs in order to obtain an improved oil recovery. So here you see the other application context where you have on the one hand the Hamilton-Jacobi equation. You have to define the velocity vector u with two components. Here is a very special model assumption you do in this very specific model context, which can be changed and adapted in other contexts. And if you plug in this model function, then in the end you come up with a Hamilton-Jacobi equation in this form, which you can then simulate. The main methodological setting is the formulation of an inverse problem that compares model predictions to observation data with a goal to obtain optimal parameters that minimize the cost function. So here you have the minimization of the cost function. The cost function is a function that depends on a set of model parameters and measures the difference between model prediction and data. The big issue is, where do you get the data from? So asking CONAF, the Chilean firefighting agency, for data, they provided images of final bushfire extensions. Such type of data are too scarce to work on parameter identification with a complex two-dimensional model, because if you have a complex two-dimensional model, the question is, what are the local dependencies? Therefore, we opted to apply the inverse problem setup to the more robust formulation of the direct problem in terms of a set of decoupled one-dimensional models that predict the fire propagation distance in all directions starting from the fire focus. The modeling is done with a special consideration of the effect of the slope. So here you have the slope line in a certain direction. The main goal is to establish a robust and simple framework to evaluate and quantify the effect of the slope. This framework can then be employed for different data sets. The height profiles are represented as cubic splines that interpolate given heights at several node positions. The slopes are obtained by calculating the derivatives. In each direction, the evolution of the bushfire is modeled as an order differential equation, where the variable measures the fire propagation with an initial condition equal to 0 in each direction. It means there's a 0 advanced at initial time. The rate of position change is modeled by the rate of spread, the function r, which depends on the wind velocity and the slope in the corresponding direction. The wind speed in a certain direction is a projection of the maximum wind speed in the right direction, which is projected to the considered direction by multiplication with the cosine of the angle between both directions. So, take a rest. Well, how to model things. A bird's eye view on the zoological garden of bushfire propagation models on the rate or speed is the following. The fuel has a major impact. The functional effect of the wind speed depends on the fuel. For different fuels, there are different function types. The effect of humidity is studied separately for each fuel, with different interpretation on how humidity is measured and quantified. The effect of slope is less considered than the effect of humidity. For each of the effects, like wind speed, humidity, slope, there are different functional forms proposed. Most prominent are exponential functions or polynomial functions. Combined effects are considered having adaptive or multiplicative impacts. In our context, we opted for the most robust choice by the use of exponential functions and their multiplicative effect. By the multiplication, we are sure that in the absence of one effect, the model reduces to a one-variable model of the other effect. The rate of speed of the bushfire propagation depends on several variables. U, the maximum wind speed, theta, the slope function that depends on the position x, phi, the wind direction. The different parameters account for different components. A, the effect of the fuel, B, the effect of the wind speed, and C, should be here, the effect of the slope. Given a rate of speed function, we can plug it into any governing equation for the direct problem. For example, a Hamilton-Jacobi equation or a system of decoupled ordinary differential equations. In order to get a feeling for the model behavior of the direct problem, we can systematically change the parameters. For example, playing with the parameter A that quantifies the fuel impact in absence of the other effects. Or assume a wrong wind direction that does not correspond to the data. Or playing with the parameter C that controls the effect of the slope. Small values underestimate the effect, large values overestimate it. If we have only one free parameter, then we can visualize for which value the cost function assumes its minimum, just like here. The cost function measures the difference between the data and the model prediction. The minimum of the cost function indicates the optimum parameter for a given model. So if there are two free parameters, then the visualization of the cost function is analogous, giving the visual hint where the optimal parameters are located. So here in the contour plot and here in the 3D plot. So what is the conclusion? What is the conclusion? What is the conclusion? Environmental phenomena with territorial extension allow the transfer of similar approaches and methods. One example is urban air contamination, which is generated by traffic, industry, or domestic heating with wood stoves, which is a major problem in the winter season in southern Chile. Within the paradigm of Internet of Things and big data, data is recollected from different sources such as satellites, a spatial distribution of sensor stations, or mobile devices. In the photo, we see a mobile sensor kit where different types of sensors are connected to a microcontroller that bundles the data to send them to a central server. For example, in urban air contamination, the most relevant sensors measure particulate material and air humidity. For mobile data collection, a GPS sensor is added. The most efficient data transmission technique is LoRa, long range. One non-standard idea is the modeling of gentrification or social segregation within a city by a system of differential equations, where, for example, the inscription process of pupils to schools is simulated by a chemotextus model. In order to obtain an accelerated simulation, our implementation uses parallel computing on a GPU using the CUDA interface. As a general perspective, we have different types of applications with a spatial dimension that can be handled analogically by the reuse of simulation methods and optimization tools. The idea is an effective reuse of concepts with an open modeling approach. A corresponding presentation within the session of open distributed modeling was already realized in this morning, so we are working on it. Given modeling and simulation concepts at hand, a common challenge of all these approaches is access to suitable data. In order to access observation data of bushfire events, we contacted CONAF, the National Forest Corporation of Chile. CONAF is an institution in charge of fighting bushfires and guarding national parks, as, for example, the Torres del Paine National Park, which I visited pre-pandemic, and so this is an own photo. So maybe there are opportunities for common projects that give reasons that you come for a visit. Maybe some of you are interested in doing a postdoc in Chile, or you know somebody who might be interested. So these are the Torre de Paine. It means tower to heaven. Or Paine is a color. So Paine is the Indian name for the color of the sky. So it means these are the towers of the sky, and Paine is a color. So Torre de Paine or Torre del Paine. So actually, to come to this place from Puerto Natales, you have to first take a bus trip 2 hours, and then you have to enter the national park, and then you have a second bus trip just to the entrance, to the hiking trail. Well, and the bus starts to return at 6 in the evening. But you have on the one hand plenty of time to do the hike, but you should maybe be sort of trained, not fully trained expert, but maybe hiking a couple of kilometers. I don't know, it should be 10 kilometers maybe in all over. So you should be sort of trained. So guess what is missing in this photo. So this photo is done on the trail towards Torre del Paine, just the other direction. So guess what is missing in this photo. It is a forest at the lake. And you might have a guess why the forest is missing. Well, the worst case is a bushfire within a national park, as happened in 2011. CONAF, the National Bushfire Fighting Agency, is in charge of fighting bushfires, but not interested in collecting data beyond the scope. They count with one single employee for all the simulation, and he's using a commercial tool. So the question is, why won't we collaborate? So why don't we set up an ecosystem for the co-creation of an open tool or open tools for the prediction of bushfires? Switching off the green screen, just have a trip. This hill is a victim of bushfire. Let us have a tour to the window. Let us look outside. So here we are in a classroom. This is a view towards the city center of Temuco, and the hill in the background is a victim of bushfire.